This is a small concept discussion. Potential due to a charged conducting sphere. Q represents the total charge on the sphere. It's a conducting sphere. Charges can move whether it is a solid or hollow sphere. If it's a conducting sphere, charges stay only on the outer surface. Radius is capital R, even it is a hollow or a solid sphere. Even you try to give charge inside the sphere due to mutual repulsion. Since the conducting medium, charges can move. The charges try to keep maximum distance away. They will stay on the outer surface. But if it was a non-conducting sphere, it's an insulating medium. Charges will stay wherever you apply the charges. Charges can't move in a non-conducting insulating medium. So the discussion may be different for a non-conducting or insulating sphere. For any conducting sphere, charges stay only on the outer surface. So capital Q is the total charge, R is the radius of the sphere. The charge inside the conducting sphere will be 0 because charges all stay on the outer surface. Since no charge is enclosed inside the sphere, the electric field inside the sphere also will be 0. If electric field is 0 inside the sphere, if you imagine a test charge small q to be moved inside, the force on the test charge will be 0, F equal to QE. Since electric field is 0, the force on the charge inside the conducting sphere will be 0. Since there is no force on the charge, the work done, the total work done or a small work done in displacing the charge inside the sphere also will be 0 because no force on the charge. So this is the basic concepts for a conducting sphere. Charges stay only on the surface. Charge inside is 0. So any charge inside, if you bring or you imagine, the force on the charge will be 0. So work done to move the charge inside the conducting sphere also will be 0. Now we are trying to find the potential. Potential at a point is defined as work done per unit charge from infinity to that point. Work done per unit charge, W by Q, for moving the positive test charge from infinity to that point. So we're finding potential at any point inside the sphere. So will be work done to move a test charge from infinity to any point inside by the test charge. Now this work can be split into two. Work done from infinity to inside can be split as work done from infinity to surface plus work done to move the charge from surface to any point inside. Infinity to inside can be split into infinity to surface work plus surface to inside. The advantage of splitting is work done inside will be 0. So work done from surface to inside, this work will be 0. So the potential inside is same as work done from infinity to surface by the test charge. This is same as a potential on the surface. So potential inside is same as potential on the surface. So potential inside, potential outside, both are same as potential on the surface, which is KQ by R, because a sphere act like a point charge for every point outside the sphere and on the sphere. On the sphere is same as inside. On the sphere, potential for a point charge is kq by r. Since a sphere can be imagined as a point charge or points on the surface and outside, the potential on the surface, which is same as kq by r due to point charge. So this in terms of charge and the radius. If we change in terms of surface charge density, charge by area is surface charge density. So charge can be surface charge density into area. Area of the sphere is 4 pi r square. So if we substitute 4 pi r square sigma instead of q, and k as 1 by 4 pi epsilon, potential inside, which is same as around the surface, will be k 1 by 4 pi epsilon r instead of q 4 pi r square sigma 4 pi 4 pi 1 r get cancelled. Comes as sigma r by epsilon. This is another expression in terms of surface charge density and radius. This in terms of charge and radius with 1 by 4 pi epsilon. The potential inside surface both are same, which is kq by r or sigma r by epsilon. Now potential at a point outside the sphere. So outside r is greater than the capital R. So already we discussed a sphere act as a point charge with a whole charge assumed to be concentrated at the center, 4 points on the surface and outside. So you can treat this as a single point charge. For a single point charge, potential will be kq by r. Kq by the distance r. Now k is 1 by 4 pi epsilon r and q is again 4 pi r square into sigma. So 4 pi will go. Sigma by epsilon r square capital by small r. That's a potential outside the sphere. So inside and on the surface is same. Outside is kq by small r for sigma r square by epsilon in the small r. So one sample question based on this. A hollow metal sphere of radius 5 centimeter, capital R is 5 centimeter. Potential on its surface is 10 volt. What's the potential the center of the sphere? Center is point inside. Potential inside the sphere is same as potential on the surface, which is same as 10 volt. Even 3 centimeter point also, that is inside the sphere because radius is 5 centimeter. So 3 centimeter also, the potential is same as that on the surface, which is same as 10 volt. Now inside the sphere, outside the sphere, there's a difference. Inside and surface are same. Outside we have a different formula. 15 centimeters outside. kq by r. So r is given 15 centimeter. We don't know q, but they given the surface potential. Surface potential is 10 volt. That is kq by capital R. So kq as a total you can get as 10 r. You can substitute kq as 10 r here. So 10 r by small r. Capital R is 5 centimeters, small r is 15 centimeters. So 10 into 5 by 15, 10 by 3. That's a final potential. Small r is given as 15 centimeter outside point, and capital R is the radius of the sphere, that is given as 5 centimeter.